Okay, thank you very much. So,
Yeah.
hear me? All right.
Yeah, so it gives me great pleasure to invite Professor Kurihara. He will talk on Kolyvagin systems of Gaussian type and the structure of Selmer.
Thank you very much for the introduction. First of all, I like to thank organizers for inviting me to such a pleasant conference. So this is my second visit to India, and my first visit was 5 years ago, also at Tata Institute, but in Mumbai. And that was also a very pleasant conference just before the pandemic. So after that, no conference, no real conference had been held for a long time. So I remember very clearly that conference in Mumbai. I really enjoyed it. And also in that conference, Dipendra and Shakha gave me their preprint, and in which they asked a question of some specific elliptic curve, the structure of the Tate-Shafarevich group. And I think my theory can answer this question, and I did a numerical computation. And so today's story is related to this kind of things. So in this, much numerical computation can be done on this story. Yeah, and okay. So 5 years ago, I talked about something like a regulator part of the Masato conjecture, but so I submitted a different paper to the proceedings, and so that's a Tata proceedings, I think. Tata proceedings, arithmetic geometry. So I wrote 5 years ago some and the first 3 chapters, first 3 sections are really a survey I wrote as elementary as possible. So concerning the talk today, good reference is this my survey paper in this volume. So this was published last year. Maybe you are the editor, yeah. Okay, so, and also after that, so much progress has been made by Chan-Ho Kim and Ryotaro Sakamoto, and also recently I received a paper from, I forgot the name, Angrel, a student of Chris Busley. So this subject is has been developed, yeah. Okay, so maybe this terminology is my terminology. So I have been working on this subject from 20 years ago. This is my terminology, but maybe recent terminology should be rank 0. That's a Ryotaro's terminology, but the same thing. Okay, but okay, introduction. Let me begin with a classical theorem by Kolyvagin. So that's a Gauss sum. So as I wrote, Gauss sum. So famous theorem by Stickelberger in 19th century is prime decomposition. Prime decomposition of the Gauss sum becomes a Stickelberger element, roughly speaking. And when Kolyvagin invented the notion of Euler system, I think not only Higner point cyclotomic units, but also such a Gauss sum had influence to him, I think. But this kind of Gauss sum Euler system is written in Rubin's book, but it's a finite Euler system and not the usual Euler system. So this had been neglected, I thought. But let me begin with the following theorem by Kolyvagin. So Stickelberger element, I have to I will talk slightly precisely. So suppose that this is a Stickelberger element, classical Stickelberger. So of course, half minus a divided by n is correct, I think. So that's a zeta value, but I use this classical. So Gn is a Garo group of so this is just the introduction, but so this corresponds to sigma A, and chi is a Dirichlet character of conductor n, and chi odd character, and not Teichmüller character, and P does so for simplicity order, or actually Kolyvagin worked on this under this assumption, but such a character, odd character I want to take, and suppose that F is a imaginary abelian field corresponding to chi, and consider the okay, I have to take P is a prime, P is a prime such that P is a prime. And so the class group, the P component of the class group. Okay. And so chi is odd, so P is not 2, but by this assumption. And the theorem of the Kolyvagin, in his famous paper on Euler system is following. So take K. Okay, M is some positive integer, and consider the class group. Okay, I have to take A chi is chi component of this chi component of this class group, chi component chi eigenspace of this class group. Then the structure of this chi component can be expressed by some element fitting ideal. So I want to use fitting ideal. He didn't use a fitting ideal, but I want to use Okai. Okai is, I'm sorry, Okai is EM is generated by some delta D, Stickelberger. So I will explain the notation. Yeah, this is generated by such kind of idea. So first of all, P is a prime. That is a prime. One more Pn. Okay, I fixed some positive integer M, and okay, no. L splits completely in F, and N, maybe I'm considering a sticker element here, so I want to write down like this way. So this is a square free product of primes in E, and also one, we regard one is in this. Then considering okay, theta n, so n is here. Let me see. No, d I wrote. Okay, d here. Then consider theta n d and Stickelberger, and taking its chi component. This can be written delta d. Okay, so n d. So I need more notation, but Okay, Galois group of the cyclotomic field ND is Gn times GD, and yeah, and GD is a product of GL, and I fix the generator tau L. Sorry, my writing is maybe small. I will try to write more larger, but okay. So this element is if D is L1 Li, then this is tau Li minus 1 modulo SPM tau L1. Yeah. Anyway, I wrote precisely, but this delta D, the important stuff is this delta D is determined from a Stickelberger element, and this is easily computable. And if you know all the fitting ideals, then you get the structure of this module. Or if you take m greater than the order of this, the PM is greater than the order of this class group, then of course PM can be omitted. So PM, this part PM can be omitted. So you know that. Sorry. Delta D is also, so I'm taking a mod PM, and this is a leading coefficient. So delta D is in OCHI divided by PM. Okay, so this is a fitting idea of the OCHI over PM. So this is the ideal of OCHI over PM. Oh, new B. That's a thank you very much. This is a number of lines dividing D. So this kind of so Kolyvagin did not write in this way, but we can formulate his theorem in this way, and so Euler system of Gauss sum. So I didn't talk about Gauss sum, but gives you complete knowledge of the structure of the class group in this situation. Yeah.
This is rank 1.
Rank 1?
Yeah, Kolyvagin system of rank 1.
Rank 1, what kind of rank?
Core
rank.
Yeah.
Core rank is, I think 0. Core rank.
Minus eigensphace is 1 dimension.
I think we have, okay. So Euler characteristic is 0, I think. So that's yeah. Anyway, yeah. So I generalized this to totally real field, and also CM field over totally real field, and also Iwasawa theoretic context. So this can be generalized. So by this formulation, so there are some condition, some minor condition is needed, but this can be generalized. Yes. Yeah. But so. Okay, why I wrote this such precisely was so people can say the structure of a class group can be determined by this, but the question, this is one of the main questions today, is how many D's we have to compute? to get right-hand side. So right-hand side, we have to consider infinitely many Ds. So in this sense, even if you compute numerically 100, 200, 300 Ds, but you might not get a good idea. So how many Ds we have to compute? That's one of the questions, and also that's the reason why I talked about this. And I don't talk about the class group. I will talk about the Selmer group. But okay. Also, Meza and Rubin. Meza and Rubin, in their book on Kolyvagin systems, some structure theorem, the structure theorem of Selmer group, general Selmer group, not only elliptic curve, but they use this kappa n. Kappa n is this Kolyvagin derivative or Kolyvagin system, Kolyvagin system. And this cannot be computed at all, I think, numerically. Cannot be computed. I mean, numerically. It's very hard. I heard this kind of thing from Carl. And so the advantage of this original Kolyvagin theorem is right-hand side is a numerical object, numerically computable objects. So, okay. So let me begin with Selmer group. So E is at first, I want to talk about a more general elliptic curve over number field today, but this is elliptic curve. And consider the Mesa Tate modular element. Yeah. So this is the usual modular element. So, okay. So F is a modular form associated to this divided by a Néron period. So I assume P on. So the difference of the two, I'm not care. So, okay. So this is in Q, again, Gn, can say, I think. Sigma is the same as before. And assume P does not divide the two and the conductor. This is just for simplicity. Several parts, I don't need this, but, and also P does not divide the Tamagawa factor. This is also, some part, this is not needed, but, okay. And also, I need this, so EQP doesn't have a P torsion points, and rho EP infinite, so this Garo representation is surjective. So that's my assumption today. And so no limit now here after after morning your talk. Sorry. Okay, very good. Then I have to take again a P like that. So that's a class group case, but the P is that's a L prime. L does not divide. L is a good prime. L is a good prime, and L, okay, fix M, and did I write correctly? Okay, this one. One modulo PM, and important condition is EFL. That's PM torsion point. It's cyclic and order P to the M. And by Chebotarev density theorem, P is an infinite set. There are so many. So you can see later some new example. Maybe I don't have time, but if I have time, some numerical example. And N is a square free product of primes in P. Okay, and the theta n, okay, theta n is as before. If I'm sorry, this is not good. If n is L1, Li, as before, I want to write down this way, modulo Q to the m, and yeah, tau Li square I, 1 to I. Yes, so leading term, and or this delta n has a simple expression like this. Oh no, my note contains several different notations. So L divided log FL A modulo ETGM, which is in a Z mod PM. Yeah, log FL is log FL is log FL is FL. So we fix primitive root of this, and this goes to yeah, fixing some generator, yeah, and yes. And okay, I assume rho infinite. So I assume yeah, surjectivity assumption. So modular symbol becomes integral, and this is in yeah, this is in Z mod PM. I think. Okay, then one of main theorem is the following, like this, but slightly different in an important point. Maybe. Okay. So I have to say, okay. I will state the theorem then first. Suppose that n is in n, and p does not divide this delta n, this number delta n. Then theorem I should write down. Assume this, and if nu n is R, then fitting ideal of the Selmer group, this Selmer group Z mod PM, and the Selmer group Q EPM is generated by delta D, where E divides N and mu D is I. So I is fitting ideal. Yes, if for all I such that, so now we have a parity. So depends on the root number. Such a fitting ideal can be described only for half of this, but half is enough to determine the structure. I is mu n, okay, mu n modulo 2. Yes. Yeah, this is generated by this. Yes. So now you will see the difference between this Kolyvagin theorem and sorry, today I forgot. I wrote in so this is a joint work with so today's talk is a joint with Yotaro Sakamoto. Yeah, this is clear that this is you can compute. It is enough to compute finite numbers of delta D because of this condition. I don't need this. I wanted to write down R here, but okay. I don't need that. I'm sorry. Okay. So let me explain a little about this. Yeah.
If you assume the Kumar Van Der conjecture, it's known as the class group situation.
No. This is a general Dirichlet character. So lambda invariant can be bigger and bigger. No. That's of course just if you get such a duality from how to say Tate-Poitou duality, then it can be recovered. But this is a slightly different direction. Yeah. Actually, it's not cyclic in general, so we can get many examples. This too. I don't need such assumption. Both ordinary and supersingular, okay. Actually, I'm working on ZP, so I will not talk about Iwasawa theory maybe. So if you consider Iwasawa theory, then we have to think about such kind of thing. But we are working on just over Q, so it's not, yeah. Okay, so for example,
This says that it's generated by delta 1.
Oh, yeah. Okay, delta 1 is, by this assumption, I assume that P does not divide Tamagawa factor or something. So, okay, fit 0 is, this says just this, yeah. Fit 0, so if this is 0, then this Selmer becomes infinite, or so for any m, so yeah. Yes. Okay. So maybe. Okay, just one example then. It was in a paper by Dipendra and Saka. So the conductor for is 42380 CI1. I don't want to write down the Weierstrass equation, and I take P equal 5. So P equal 3 can be also applied. So, but this example, they asked a question, the case P equal 5. Then this number, LE1 divided by omega E. So I was asked this. So this is this. And so even if you prove the Birch-Swinnerton-Dyer conjecture, there are two possibilities. So Tate-Harwich, this or this, okay? But take m equal 1, take m equal 1 and consider such kind of P and N, then P, I can compute numerically 41, 191, blah, 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 this kind of, and also we can compute. So just a computation of modulo 5 is okay. So in this case, so it's not so difficult. So I'm not good at numerical computation, but even for me, this can be computed using Sage. And so 5 does not divide this first one. Okay, then this theorem says that fit 2 is a whole. So this means that, okay, SHA has to be, so this is generated by 2 elements. It's a 5 component. 5 component has to be, is this. So we can show this. Also, this part is a Tamagawa factor. So wholes, if you if you work other primes, then this is a whole Tate-Saharovich group. So Tate-Saharovich group is like this. Okay. And concerning this assumption, this was a, yeah. This was a conjecture of mine, but Chanho Kim, Chanho and Chanho Kim and Sakamoto, independently, I think, proved that this is equivalent to the Iwasawa. Oh, I said I don't use the Iwasawa theory, but I have to write down Iwasawa conjecture, but Iwasawa conjecture for E and cyclotomic ZP extension. That's a cyclotomic ZP. So numerically, you can find such an n like this, And this is also, okay, I want to explain it more. The case, okay, case semicolon. The case semicolon. So corollary is the following. If NM, okay, need more notation. The case, we say N is delta minimal if P divides delta D or any proper divisor D of N. And so conjecture says, or if you believe that Iwasawa conjecture is proved in many cases, so almost proven. So we can find such kind of N. And corollary is if NM are both delta minimal, because this theorem, then this number of prime divisor should be equal. So this kind of thing never happened in class group case, and also, yeah. So maybe I should say that kind of thing. Take okay. Important thing is the class group case, so which I mentioned in the introduction. This never happens. For example, take a chi. So this was a Dirichlet character. I take this is a conductor 23. Then So Legendre symbol. Then F is Q square root of minus 23. Then and we have to take P equals 3 because almost everyone, as almost everyone knows, this class group is Z mod 3Z. So then I can compute such a prime, Kolyvagin primes like this, so many. And but for example, that similar thing happens. For example, actually, P does not divide the delta 13. So from this, we know this is cyclic. So from this, we get cyclicity. But if I forget this, then if I'm strange, then if I suppose I first compute 151 times 211, then this number does not divide by 3, and also 3 divides both 151 and 121, 1 to 11. So this is a I don't define for secret element the delta minimality, but this is if I define the same way, then this number is delta minimal, and this should, if this theorem holds for class group, then this class group should be not cyclic, but reality is that this is cyclic. So this never, this kind of theorem does not hold. So this is a interesting point of the elliptic curve. The reason why that difference happens is that Tate module, Galois representation, the self-dual in the elliptic curve case. And for self-dual motifs, we can get such kind of good numerical theory. That's in some cases, and this elliptic curve case is actually one of them. Yes. Okay, so maybe I talk too much. So I don't want to. Okay, but just one. I will talk a little. Yeah. So. So consider the following homomorphism. So I'm still working the case m equal 1. One case. Consider so this is a Selmer group. So if you take let me see, H1, if you go to H1QL, okay, Ln H1QL, E, or E to the P, then this should inside EQL divided by P, and this is same as in this case EFL divided by P. So we have a map from here to here. That's and also here inside here we have a model Bay group. So we have a sometimes status average group is its average group vanishes. So about 17 years ago, I computed. So this is just a reduction model, and take such a and let me see. Suppose IMC for T to infinity holds. So then this map, reduction modulo n I call Rn. Theorem is Rn this quite a elementary map. Rn is bijective if and only if it's delta n is zero. In FP, I should say. So such equivalence, for the first time, so computing numerically this map, I surprised because this never happens for class group case. And but elliptic curve case, this seems to be equivalent. So that's a starting point of this theory. So I wanted. So now this is just a main conjecture proof, and this can be proved. Yeah. Okay. So. Sorry. I'm sorry. I need an assumption. So dimension, suppose IMC is through and the dimension, Selmer Q, EP is a dimension, FP dimension, E dimension is equal to UN. Then delta minimality is not needed. Okay, then I want to talk about why this kind of thing happens. So Chanho has a different method, but our method is following. So Kolyvagin system of the Gauss sum type in my title. Okay, so to explain this, I need a Kolyvagin system. That's a main ingredient of the proof. I need a map for L. For L, delta L, the H1Q EPM to H1QL EPM divided by this finite part. And this is by local Tate duality, and this is same as this. So for such L, EFL EM is Z mod. So I fix some base of this. Then okay, so I can say FL. We have so I fix for all L this isomorphism. Then we have this kind of map. But this is just a usual map corresponding to the variation. But and PL is a map H1, H1Q EPM going to H1QL. But now the local condition changes, and this is Maser-Rubin's local condition, H1 transverse condition, and then this is equal to EQL, EFL over PN again, and I must. So we have a map. So H1 transverse is a kernel of H1QL EPN to H1QL UL EPN. So that's the theory of the Maser-Rubin. And then theorem 2. Theorem 2 is for any NL such that NL is in N. There exists a family kappa NL. So NL is in P. No, N. Kappa NL is an element in H1 Q over E bracket PM. Yes. So four properties. Delta R kappa NL is 0 for any prime R which does not divide NL. One. The first property is PL. So this is a usual Kolyvagin derivative property for any prime R dividing N. And PR kappa NL is delta N. So this delta N is coming from modular symbols. 3. PL kappa NL is 0 for any. No, I'm sorry. Dividing N. And PL kappa NL is a minus delta N. This is also defined by modular symbols. So in my paper in Iwasawa 2012 volume, I under some conditions, assuming some conditions on N and L, I show the existence of this kind of element. But now no condition is needed. So so to prove, I think the theorem the first theorem. Usually Chebyshev density is needed. We use just a Chebyshev density, so we don't need every NL. But now we have for any NL. So I'm assuming some conditions. Then we have this. Another condition still this. So I thought at that time such an element should exist always. But now we can prove this by a different method. Yeah. And okay, so let me explain why from this first theorem. So first theorem is proved. So that's for example, Selmer. I don't have so much time, but okay, but this is not good, but this terminology is might not be good, but this is something like etal, but etal, maybe I should write down this way, but cheat some notation. And so we have a localization sequence which appeared in my previous speakers localization sequence attached for to duality. Going to yeah, Selmer, you EPM, you are yes, and we have a map from here. And this is by definition free Z-mod PM module of rank nu n. And this is also yeah. So that's yes. If he does not divide the delta n, then this becomes bijective, and we can show that this is bijective. And so this Selmer group has such a free resolution as a Z-mod PM modules, and this kappa NL gives a standard basis of this. Not standard, not one, but this gives a linearly independent element. So this gives a basis of this. And we know this map by this property. So this is not a proof at all. So this is not enough at all to prove this theorem. But this gives you some insight why this kind of thing is helpful, I think. And for theorem 2, we take a stack system, and this kappa NL is constructed as the image of the stack system. But let me, maybe this is not, okay. Rank 1 stack system I want to consider, and take some map to a rank 0 stack system, and take an image of this rank 0 stack system, and construct this way, very, very big construction. Yeah. Okay, so since I have only 10 minutes, let me talk a little bit about more generalization. Yes.
Go to infinity.
I'm considering just a finite Selmer group here, but if you take m infinity goes, if m goes to infinity, then of course you get information of. Is this your question? You get information of this too, and so if theta Shahrovich is finite, then this is isomorphic to EQ. Yeah. So we get the information of the rank 2 from this delta n, delta d. Also, I'm fixing E. I'm fixing E, and
the middle things become an isomorphic.
I'm fixing E here. Yeah. So just this is just a localization sequence or a Tate-Poitou duality. And so maybe I will talk. So this is a theory of a rational elliptic curve, but this can be generalized to a higher weight modular form of gamma 0n, and Chan also. He made many, I think, results, but this story can be generalized. So self-dual motifs. So let me consider the K is a number field, and E is an elliptic curve. Okay. Okay. In this situation, I wanna consider elliptic curve. Yes, and I assume P does not divide U and the Tamagawa factor, and again the same. I need this under Roy infinite surjective. Then Okay, then theorem 3 is the following. So then, okay, I forgot the, okay. Maybe I have to say, we say, oh, it's time? 5 minutes maybe. I think, yeah, I still have 5 minutes. Okay, so we say kappa NL and delta N. This is a Kolyvagin system of rank. Sometimes today I use my older terminology. Gaussian type if it satisfies the condition of theorem 2. So in theorem 2, this delta n was some specific element, but in general, we can consider this kind of element. So we can consider more equivalently, but now today I'm considering just H1, kappa n is just H1k of E PM, and delta n is just G mod Pn. So if such elements satisfy this, then this is called the Kolyvagin system of Gaussian type. We define that to be then theorem 3 is there exists Kolyvagin system is kappa NL and delta n, by which we get a structure theorem. As theorem 1, so structures of cell A, EPM as theorem 1. Maybe I didn't number the first theorem, but you understand what I mean. And if at least, but the problem is that this delta n, we don't know what they are. So so we need information on the L values, but in such a general situation, we cannot do that. So if at least A is totally real, maybe this assumption is not needed, but totally real. And ETNC, okay, this is a Bloch-Kato conjecture conference, so equivalent to Bloch-Kato conjecture, I should say, but ETNC holds, then delta n is described by L values. Yeah. So let me remark that. So in this situation, Euler's system should be an element in exterior bidual. So if Okay, D is the degree of the number P. Then Euler system should live in such a, what to say, H1, P, yes, T is a theta module. ZP. Yeah, exterior ideal. So we certainly need or if you take a tensor Q, then this is the same as the wedge product. But Euler system or Kolyvagin system, if you have such a Euler system, then you get a Kolyvagin system in a usual sense. But this also live in such an exterior ideal T over PM, maybe. Yeah. No, small k. Yeah. Kolyvagin derivative in a usual sense from the Euler system, usual Euler system, is in such an exterior ideal. So, but our Euler system lives in this Euler system is not in exterior ideal, but in real Gauss cohomology. Yeah. So in this sense, this is in some sense interesting phenomena, I think. But this is a work in progress on what kind of so maybe total real is not need something. So in a general case, yeah, formulation would be different. I know, for example, if you take an imaginary quadratic field and consider the anticyclotomic direction, for example, then in such case, this relation with L value is should be formulated in a totally different way. So anyway, okay, just okay, this notation was introduced by one of my students, Takamichi Sano. I disliked this notation, but now many people are using. So for R module, this notation means that M star, where M star is is a linear form. So R, MR. Yeah, this works very well. This, rather than usual exterior power and theory of Euler system and Kolyvagin system, stack system should be used using this. So this is such a theory is created by David Barnes, Takamichi Sano, and Ryotaro Sakamoto, and we have such a higher rank Euler system, but yeah, Meza and Rubin began such a theory, but now Barnes, Sano, Sakamoto's theory is very beautifully created. Yeah. And so such a Euler, what I wanted to say was my Kolyvagin system is different from this kind of stuff. So, okay, I stop here. Thank you very much.
When you said that, then right, like in right use, you mean
I mean, in a totally real case, L equal. That kind of thing. Yeah. Character. Yeah. Oh. We are using it. So
yeah. But not the other way around.
So we cannot recover the explicit reciprocity law. Or is that your question? No?
So like Kato has his divisibility towards the main conjectures, and since you have some sort of Euler systems, whether you can reduce that-
converse. No?
just
No,
the
no.
just
Just a divisibility. Okay. Okay. I didn't think about this. I only consider such a simplest case over Q. So we have to consider equivalent ways and let me see. Yeah. I see. Yeah, such kind of thing. Yes. But I'm afraid that this is a different proof because we are using Kato's theory too.
Yeah.
So Kato's, for example, lambda torsionness of the Selmer group or such kind of things. So I'm afraid that's new. So I'm afraid. Yeah, that is not new, I think. Yeah.
We work over general number field K.
Yeah.
If we don't know like a modularity, how can we describe delta n? Like
No. So what I wrote here is ETNC. So
okay.
ETNC gives you some information, the relationship between my Kolyvagin system and L values. So that's why I wrote L values.
Okay.
So it's not a modular element. It's not an integral of the modular form, but L value. But modular element is also described by L values, I think. So in this sense, yeah. Tell me. For number field case?
Yeah.
Uh,
No, for
Q. Oh, yeah. If I know the main conjecture, then but theorem one is over Q, so I have a complete theory, I think.
Are there any other questions? Okay, let's thank the speaker again.
Thank you very much.